All of organic mechanism can be neatly summed up in two fundamental facts. And those fundamental facts are that in a chemical reaction, there are two fundamental processes. One process is that of bond breaking, now, of course, from earlier in this unit, we know that bond breaking is an endothermic process. And by endothermic, we mean that energy is going to be required. Just a quick example that illustrates this idea. If you look at a potential free energy diagram of any chemical process, you will always notice that you will have a curve that is like this or similar to this. We're mapping potential energy as a function of reaction progress. Literally the time from the beginning of a reaction until that reaction is able to attain chemical equilibrium. Notice that the first step of this reaction always increases the energy of the reaction. So this zone that I am going to highlight in purple is bond breaking. Of course, there's another part of this equation, and that is I will have bond making. And bond making is an exothermic process. In other words, energy is released. And so the bond making portion of this reaction curve will be rendered in orange. In any organic mechanism, we are going to push arrows to show bond breaking processes and bond making processes. There are some repeatable patterns in mechanism that we see over and over and over again, and they take up one of four broad classifications. And so if you look at the bottom of PowerPoint slide 644, you see that they are nucleophilic attack, loss of a leaving group, proton transfers, which means acid-base, or rearrangements. I think rather than going through each of these examples individually, it would be much more interesting to show you a reaction mechanism in which we mix these different types of processes together. And I'd also like to make it relevant. So let's look at a mechanism that I'm going to be introducing y'all to either the end of this week or the beginning of next week. So I'm going to begin with this particular substrate. Of course, notice that this is an alkene. And let's take a moment to name this alkene. I've got 1, 2, 3, 4 carbons in the longest chain. and we need to label these carbons such as the alkene carbons are low as possible. So 1, 2, 3, 4. This would be 3-methyl. One butene. And I am going to react 3-methyl-1-butene with a strong acid, HBr, and obtain a unique organic product. And so really our focus needs to be, what are the sequence of steps? What makes the most sense? And in all honesty, this goes back into the identification of the most reactive nucleophile and the identification of the most reactive electrophile. So let's just start with a blank slate. My major organic reactant, and of course my major inorganic reactant. Anytime you see a strong acid, the hydrogen that is most easily removed from that acid will always be the most reactive electrophile. And the pi electrons, because they're loosely held, in other words, that bond is not very strong, will be the most reactive nucleophile. And from pushing arrows, again, the most reactive nucleophile reacts, makes a bond with the most reactive electrophile. So in terms of pushing arrows, the pi bond breaks. I make a carbon-hydrogen bond, and the electrons that were shared between hydrogen and bromine now go to bromine to generate bromide. Now we have a choice. One of these carbons is going to obtain the hydrogen. And you have to remember on carbon 2, there was already a hydrogen. And on carbon 1, there were already 2 hydrogens. So in the beginning, I think it's useful to write these bonds a bit more explicitly so that you can clearly see that one possibility is when the positive charge resides on carbon 1. Also, we have another possibility, and that is for the hydrogen to be bonded to carbon 1 and the positive charge to be on carbon 2. Now, we want to take the time to classify these carbocations. By the way, this step that we just performed is best classified as a proton transfer. You could also term it as an acid-base mechanistic step. Now, I have generated 2 carbocation intermediates. One is going to be more stable than the other. Notice in the carbocation to the left, the carbon bearing the positive charge is bonded to one other carbon. Therefore, it is a primary carbocation. The carbon bearing the positive charge in the structure to the right is bonded to two other carbons. So it is termed a secondary carbocation. Remember that carbocations have a p orbital that is unhybridized, unmixed, and unfilled. And the more carbons that are bonded to this carbon, the more electron density that can be weakly donated to that empty orbital. The ability of this donation is called hyperconjugation. The more hyperconjugation you have, the more stable the carbocation. And previously we had discussed in class that benzylic carbocations were more stable than allylic carbocations, more stable than tertiary, more stable than secondary, more stable than primary, more stable than methyl. In fact, we've never really observed primary or methyl carbocations in nature. Secondary is going to be formed preferentially over primary. So in this mechanistic step, this is our observed intermediate. In the second step of the mechanism, we had generated a nucleophile from the first step, and that's Br minus. Br minus is now our more reactive nucleophile. While the carbocation is most definitely our most reactive electrophile. Remember, the best, most reactive electrophiles are Lewis acids, and the best, most reactive nucleophiles are Lewis bases. In other words, the electron from the Lewis base attacks the empty orbital bearing carbon of the Lewis acid to generate a new product. In this case, the product is 2-bromo, 3-methyl butane. This squiggly line I will amplify later once we do stereochemistry. It has to do with whether the orientation of that bromine will be coming towards you out of the plane of the screen or going away from you into the plane of the screen. And quite simply, we haven't discussed that yet in class. Step 2's mechanism type would be best termed nucleophilic attack. So this reaction is 2 steps, the first step of which is a proton transfer, the second step of which is nucleophilic attack. Now let's take a moment to go back to our PowerPoint, and we have introduced mechanism step 3 in step 1 of our example, and mechanism step 1 in step 2 of our example. Let's now take a look at what loss of a leaving group would be, and also what a rearrangement would look like in the context of a real example. So I'm going to start with a completely different example. We will be learning this type of mechanism very shortly. It's better known as an SN1 reaction. This particular reaction mechanism is going to consist of two steps, one of which is going to be the loss of a leaving group, which is new. The second of which is nucleophilic attack, which we've already previously seen. In the loss of a leaving group, a bond breaks. Of course, that is going to be an endothermic step. Br minus is going to be generated. You get a carbocation intermediate. So loss of a leaving group. And in the second step, nucleophilic attack. Which we've already seen. So going back to our PowerPoint, now we've seen 3 of the 4 examples. In this last example, we saw step number 2 occur first, loss of a leaving group, and then mechanistic step 1 occur in the second and final step, nucleophilic attack. I want to go back and look at one other kind of SN1 reaction and string together all 4 of these mechanistic steps in one reaction mechanism. I want to make one small change here. So my 2 major reactants are cyanide ion and 1-pentanol. I'm going to do this under acidic conditions. So I'll also have hydronium. In the first step of the mechanism, the best nucleophile is one of the lone pairs belonging to the oxygen atom of my alcohol. And I'm going to already write the hydronium in terms of its chemically active form, which is just H+. In the first step of this mechanism, I'm going to have a proton transfer, or an acid-base reaction. The purpose of this is to produce a better leaving group. We will talk about this in the future. And by the future, I mean in about a week. And I'm going to make one adjustment to my substrate. So the first step is proton transfer, which I'm just going to keep track of that over here. proton transfer. In the second step, I'm going to have loss of a leaving group. This bond is going to break. So step 2, loss of a leaving group. Step 3, I'm going to have a rearrangement. In a rearrangement, you can either have an alkyl group or a hydrogen that moves with its electrons to make a more stable carbocation. Notice if I have this 1,2 hydride shift, and I denote a hydride shift with a curly arrow. I'll let where the electrons were, where the electrons are going. And my carbocation was a primary, but now it is a tertiary, which is much more stabilized by hyperconjugation. So in the third step of this mechanism, we have a rearrangement. Finally, in the last step of this mechanism, we're going to have nucleophilic attack. This will alleviate the positive charge and give me my new organic product. So step 4 is a nucleophilic attack. Now, this reaction is unusual in that it uses all 4 motifs. You will not see this very often. I simply wanted to show you how we can string together these motifs when circumstances dictate in order to justify the formation of a product. Now that we've done this with regards to a reaction in context, let's now take a step back and look at our PowerPoint and see if we can't give a better foundation in terms of these occurring one at a time in an isolated system. Just know that what I've just shown you is nature. It's real life, it's reality, it's how it's going to occur in the context of a reaction. What the PowerPoint shows you, what your problem set wants from you, is as though these occur as an isolated event. They do not occur as an isolated event. The driving force is always going to be to make a lower energy product or a product that increases the entropy of the universe, or both. So going back to the PowerPoint now, let's begin to look at these individually. Again, remember that the most reactive nucleophile attacks the most reactive electrophile. So here, Br- attacks the carbocation. Again, nucleophile, Lewis base, electrophile, Lewis acid. So the Lewis base makes a bond with the Lewis acid. The driving force for this, of course, is the minimization of energy. Entropy will decrease because I'm going from 2 molecules to 1 molecule. Here's another example of nucleophilic attack. Now this time our electrophile is an electropositive carbon in a carbon-oxygen double bond. Notice tail of the arrows where the electrons were, tip of the arrow where the electrons are going, number of heads on the arrow, number of electrons that are moving. It's a double-headed arrow. Therefore, 2 electrons, the lone pair on the oxygen, is moving so that now you are sharing this lone pair as a covalent bond between carbon and oxygen. Loss of a leaving group. This is going to be an endothermic process. So not only can we justify a reaction in terms of what happens to the energy overall as we go from reactants to products, but we can also look at it in each chemical step. In the previous example, it was driven by low energy. In this example, it is driven by high entropy. Breaking a bond is going to be endothermic. But when I go from 1 molecule to 2 intermediates, that increases the entropy of the system. And increasing the entropy of the system is a valid driving force. Proton transfers. Best base reacts with the best acid to make a bond. So you're making 1 bond, but you're also breaking 1 bond. You go from 2 molecules to 2 molecules. So it's ambiguous whether the energy is being lowered or the energy is being raised, whether the entropy is being raised or the entropy is being lowered. You would actually need to look at a table of thermodynamic parameters to determine what the driving force is. And it's possible that a step could have a positive delta G, so long as that there are other steps that when you add them make the overall process a delta G that is less than 0. Carbocation rearrangements. Remember, hyperconjugation means this carbon, which has a partial negative charge, can weakly add electron density to this empty p orbital that is unhybridized. The more carbons there are, the more easily it is to stabilize this intermediate. As such, tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations, which are more stable than methyl carbocations. Also remember what I said earlier. These essentially, primaries and methyls, have never been isolated in nature. So we can have shifts from 1 carbon to an adjacent carbon. That is called a 1-2 shift, where the atom and the electrons that are participating in this hydrogen-carbon bond move or shift from the carbon that is neutral to the carbocation. This means the carbocation shifts from a secondary carbocation to a tertiary carbocation. You can also have alkyl shifts. Notice secondary carbocation, tertiary carbocation. If you don't make the carbocation more stable, then the rearrangement will not occur. And now what the line that they're taking in your PowerPoint notes is simply combining steps. For example, acid-base or proton transfer, loss of a leaving group, rearrangement, nucleophilic attack. In fact, this one is really similar to the example that I gave you earlier in this particular Ozzcast. Again, proton transfer, loss of a leaving group, rearrangement, nucleophilic attack. So I think this is a good place to stop this particular podcast. This gives you plenty of meat on which to chew. We now need to apply this type of problem solving to the problem set that I will be collecting either on Wednesday if you're in my Monday-Wednesday class, or on Thursday if you're in my Tuesday-Thursday class. Again, feel free to come see me in office hours. I'm available tomorrow from 2 to 5. I'm available Thursday is a little busier than tomorrow, but technically I'm free from 9 to 1. So the next podcast I'll be posting will deal with some more specific mechanisms that we'll begin to study towards the end of this week and the beginning of next week.